Hello everybody, welcome to another video. Today we're going to look at data modeling. All right, after today we'll be able to find equations of best fit and choose the best model for certain data sets. Okay, so some good real world applicability going on with this lesson. Okay, so let's hop right into it. Okay, our concept, our equations of best fit. Okay, these are equations to help analyze data patterns between variables. Okay, so if I'm given some data set here and I were to graph it out, okay, what you see here in black dots, that's what we call a scatter plot. Okay, so our scatter plot are these black dots, right? Okay, and then we have this line of best fit here, but it could be a curve of best fit here in the red. Okay. So some considerations with these, okay, we're going to consider slope, okay, do we have positive or negative slope for the line, okay, and we refer to that as the direction when we're talking about these data sets, okay. So we're talking, if you hear direction, kind of think, okay, as x increases, what is y doing? Is y going up or is y decreasing, okay? So for this example here, as x increases, our y decreases, so we would say that this has a negative direction, okay? And then we have form as well. Is it linear or nonlinear? Okay, so this is clearly a linear equation of best fit, but you might have quadratic or you might have an exponential, okay? So it just depends on what your data set looks like as far as the form, okay? And then our correlation strength, okay? We're thinking, how close are all of our points to our equation or line of best fit? Are they really close to it, or are they scattered all over the place? Okay, so here they're pretty close. They can definitely be closer, but this would be kind of a medium strength correlation. All right. Okay, let's continue on with this regression line or regression curve. That's kind of what we're talking about with these equations of best fit. Okay, it's the line or curve that we get from our equation. That's what we call our regression line or regression curve. Okay. Okay, so some considerations here. Okay, you can have all sorts of forms with our regression curves, right? We can have a linear line. Okay, that'd be a regression line. We can have a quadratic curve, an exponential curve, a logarithmic curve, or a power curve, okay? So if I have a data set here in blue, all right, and then this would be, say, our line of best fit for this data set, okay? So this would be a regression line, okay? But we can have more accurate estimations with these regressions, okay, if we then apply a curve to them. Okay, so instead of using a line like this, we're going to go ahead and use a curve like this, okay? So this is going to be a different shape, right, instead of linear. However, you can see that our correlation strength is a lot stronger in this second example than when we use a line here, okay? Okay, which brings us again into correlation. Okay, we have our correlation coefficient, which you may have seen before, that is a little r. Okay, and that's just showing us how well a data set is modeled by a given curve. Okay, and we're going to get r from our graphing calculator, so we're not going to have to calculate r on our own, thankfully. Okay, so some considerations around correlation. Okay, again, we have positive correlation. As x increases, what is y doing? Okay, as y increases, then we have positive correlation. Negative correlation, as x increases, if y decreases, we call that negative correlation. Okay. If we have perfect correlation, then our r is going to equal positive or negative 1. Okay, positive or negative 1. And if we have no correlation at all, then our r value is going to be really, really close to 0. And that just means that our data is like really random, and it doesn't really fit very well with whatever regression curve we're trying to use, okay? All right, and then we will see that your calculator will give you a value for r. If that value is greater than or equal to 0.8, okay, then it's going to be a strong correlation. And if it is below 0.5, then that's going to be a weak correlation, okay? So if you're asked to describe correlation given an r value, then you would want to use those values right there, okay? And going back to our last slide, okay, this would have a very weak correlation, so a very low r value, where the where the absolute value of r would be pretty close to 0, okay, or closer to 0 than, say, this r value, which is going to be probably a lot closer to 1 in this instance, okay? Okay, so that is our correlations. Let's go ahead and take a look at some examples. Okay, first example, we are asked to just describe, not define, or just asked to describe the data set that we have here. Okay, so we're given this table. It shows the cost of a smartphone in different years, all right, between 2012 and 2016. And we're given the cost, we'll say in dollars, that's fine. Okay, it says graph the data and describe it. Okay, so we're asked to describe direction, form, and strength. Again, if it just said describe the data, you would want to give at least direction, form, and strength. Those three things are your minimum, okay? Okay, so this is what our data looks like, okay, when we graph this out. Okay, so now we can go ahead and when we're thinking about direction, form, and strength, we're going to want to try to just kind of impose a regression line or a regression curve on our data set, okay? Now, when we do this, okay, that's going to look something like this. All right, now I don't know what this equation of this line is, but I can see that there is some line estimated as a line of best fit that's going through my data set, and I can see that all the points are pretty close to it, right? Pretty close. Now again, think in direction. As my x increases, what is my y doing? Well, that's increasing also, okay? So think of that as slope, right? So I have this positive direction. The form we can see is linear, right? This is clearly just a line. And then our strength here, I would say this is pretty strong, and we're not going to correlate, or we're not going to find an r value yet, but we will next slide. But I would say this is a strong correlation because of how close all of our data points are to this line right here, okay? So if you were asked to describe this data set, I would say linear, positive, and strong correlation, okay? All right. Now, we're going to use the same data set, but we are going to find the equation for the line or curve of best fit. So let's go ahead and jump into our calculator. All right, taking a look at our calculator here. Okay, first thing we need to do is input our data. All right, so to input our data, we are going to go to Stat, Edit, okay? And I've already input the data here, but all you would do to input that data would be, you'd input all your X's for L1, and for list 2, you would input all of your Y's. That's what this represents, list 1 and list 2, okay? So to input, say, this 2012, I would just put 2012, and it comes here on the bottom. So this is list 1, element 1, okay? And then you would hit enter, and then it's just going to drop you down to the next one, and you can keep inputting all your years, hit enter, and it'll just drop you all the way down. And then you can go to list 2 by just arrowing over, and you can do the same thing. Every time you're done, press enter, and it'll drop you down to the next element of that list, okay? Now, this is important. You want to make sure that you hit second and hit y equals in stat plots. You want to make sure that this is on, okay? So if it is off, if it's off here, then you're going to want to make sure that it is on, okay? Ours is on, so we're good to go. So we can go ahead and say, come back to our home screen. We're going to go Stat, come over to Calc, and then we're going to come down here to, this is where we can find all of our regressions, okay? This REG, that's regressions. We have linear regression, which has AX plus B, okay, or MX plus B as we think of slope-intercept form. We have quadratic, cubic, quartic regressions, and so on, okay? We even have natural log regressions, exponential regressions, okay? So right now we're just going to use this fourth one, linear regression, okay? And if you go ahead and click enter, okay, it's going to say X list and Y list, okay? If you don't have anything on here, hit clear so you guys can see. If you don't have anything here to access your list, what you can do is just hit second and then come down here. You see L1, 2, 3. You can just hit L1, and that's going to bring up list 1 for your X list, okay? And same thing for your Y list, okay? And then come over here to store regression. Okay, this is going to generate an equation for us, which is what we're looking for, which is great. But we don't really want to lose it, okay, because it's just going to give it to us on a window. Okay, so we're going to hit vars and then scroll over to y vars, hit function, and then we're going to just store it in y1. okay? So we could have stored that in any of our y equals. So that'll store when we hit y equals, you know how you have y1, y2, y3, that's going to store it in y1, okay? And then I can come down here and hit calculate, and it's going to give us all this information, okay? So this is great. We have r squared, okay, and we also have r values. Okay, so we have a very high r value that's very close to 1, so we know we have a very strong correlation. And then it also gives you your generic equation, so y equals ax plus b, and then it tells you what a and b are, okay? So y actually equals 116.725x minus this 234,549.866. Okay, so that, if you input A and B, would be the answer to our prompt here, okay? And we can go ahead and take a look at the graph of this. Okay, so if you hit graph and you don't see anything, first off, if I come over to y equals, you can see that it's stored my equation in here, which is great. That's what we wanted. Okay, but then if I come over to graph and I don't see anything, well, that's because we want to go ahead and hit zoom. And then we're going to go to 9, zoom stat. Okay, that's going to show us where our stat plot is being graphed. Okay, that's going to give us a good window to look at. Okay, so from here, if we were to say trace, okay, it can trace through your stat plot, or if you hit up or down, it'll then trace through your linear regression line. Okay. So if I were asked to find the, let's say we go second calc, we say we want to estimate the value of a smartphone or the cost of a smartphone 6 months into 2013. Okay, we can see what it's kind of going to be, but let's go ahead and hit second calc, calculate a value. We'll hit 2013.5. Okay, it's going to give us 6 months in, and I'll hit enter. And we can see here that a smartphone 6 months into 2013 is going to cost us about $475.92. Okay. Okay, so this right here is our equation that we were looking for. Okay, we were asked to find the equation, so let's jump right back into our PowerPoint. Okay, having a look at our table again, and then we can see that last window that we looked at with our equation right up here. Again, we can see the makings of this equation here when we had originally clicked that linear regression function, okay? And then, so again, to finally solve this and to give the equation that we're looking for, that would be y equals 116.725x minus 234,549.866, okay? And I'm just getting that from our A and B values here. Again, plugging those into this generic equation, all right? So that is how we can find the equation or line for the line of best fit. And again, if we were to graph this out, our scatter plot, and it didn't look linear, then that's when we would want to pick a different type of regression, which is what we're going to look at with our third example, okay? Okay, example 3. Okay, Tim wants to run a 15K race. He's got 20 weeks to train. He's going to track his progress and run a race every Wednesday and Thursday. This table shows the results, his best time for each week. Okay, at the end of 7 weeks, he's going to stop tracking his progress because sometimes keeping track of numbers is difficult. Right, Tim? I know, bud. And so he just stops at 7 weeks, but he's going to keep training because running is less difficult than keeping track of numbers sometimes, all right? So we have our 3 questions we're answering here. Is Tim going to be able to run the 15K in 20 weeks? And if he can or if he cannot, approximately how far will he be able to run? And then how many weeks will it take him to confidently run the 15K? And will Tim be able to run a 20K race in 6 months? We're answering all 3 of these questions here, okay? So let's go ahead and jump again into our calculators so we can go ahead and solve this one. All right, we're back into our calculator now, so we're going to go ahead and hit Stat, Edit, and I just cleared out our list 1 and 2, so we can go ahead and input our weeks 1, 2, 3, all the way to 7. Okay, and then I'll scroll over and we'll input our distances, okay? We're just taking this info right off of our table is all we're doing. So again, on list 1, we've got the week numbers, and on list 2, we have the distances, okay? So what we're gonna do here is we need to kind of figure out what this data looks like and what form or what type of regression is gonna be best for this case, okay? So if I go to, let's see, if we go stat calculate, we're gonna go, we can try linear regression first. Let's try that. Okay, we'll keep list 1 and list 2, and we'll just go ahead and hit calculate, okay? So we can see we have an R value of 0.8777, all right? So let's see if we can beat that at all. So we'll go ahead and hit stat, calc, and we'll go down. Let's do quadratic regression, okay? Enter all the way through, and we'll calculate that. All right, so now we have an R squared value. We have an R squared value of 0.834567. All right, so since that's R squared, I need to go ahead and calculate R. Okay, so let me just do that real quick on the calculator. So 0.8345679012. Okay, so that gives me an R value of 0.9135. Okay, so that's pretty high up there, right? 0.9135 is our time to beat, okay, or our R value to beat, rather. Okay, so we'll go stat, calc, we can do a cubic regression. Okay, calculate that. Okay, again, we're given an R squared. Okay, so let's go ahead and figure out what our R value is. So 0.8678062678. Okay, so that's going to be just under our quadratic. Okay, and then we'll go ahead, go back to stat, and we can try, I don't know, we can try maybe a logarithmic one, just for fun, and we'll get in. Well, we haven't gotten into logarithms yet, so let's stay away from that one. Okay, maybe we'll try an exponential regression. Here we go. And we'll calculate that. Okay, 0.8488. All right, and then we'll hit stat, calculate, maybe quartic. .2. Okay, so 9.3 is looking like our best one. Okay, so I'll go ahead and hit stat, and we'll go calc, and that was, I think, our quadratic was the best. So we can go ahead and store this now. We're going to store this again by hitting vars, y vars, function, and we're going to store this in y1, okay? And then we'll go ahead and hit calc. Okay, so now I'm given this whole equation here, okay, this cubic or this quadratic equation. And then if I go to y equals, it is stored right there for us, all right? You can kind of scroll, oh, that's fine. Okay, so now we need to go ahead and graph this. And if we graph it, again, this looks like nothing is going on. If you have the standard window up, then you can kind of see we got some stuff going on here. Okay, so we'll go zoom 9 for zoom stat and hit enter, and we can see what we got going on here, okay? So from here, let's go to our window, and since 20 weeks was what we were looking for, we'll hit 20, and our y minimum is going to be 0, and maximum will also be 20, okay? And we'll go ahead and graph that. All right, so now we were asked to find if Tim is going to be able to run the 15K at 20 weeks. So what we can do is we can say trace, and we can make sure we are tracing our curve, our regression curve, okay? And then we're just going to go ahead and hit calc, the value at 20 weeks, and we can see that no, Tim will not be able to run the full 15K in 20 weeks. Okay, so let's see, what was our other, how many weeks will it take him to confidently run the 15K? Okay, so in order to do that, I think it's 22. So if you go ahead and hit second, calc, you can try out a bunch of different values. We just go up by 1. But if you go up to 22, okay, so we can see we had to extend our window a little bit, but we can see that at 22 weeks, Tim will be running over 15K, so that will be where he can run confidently that 15K race. Okay, and then will Tim be able to run a 20K race in 6 months? Let's go back to our... Okay, so in order to answer these, first we said when x equals 20, and again we are just looking on our regression curve, okay, because our data points end before 20 weeks, right? So now we just have this curve to estimate where Tim's going to be. Okay, so we can see that he's not going to be able to hit that 20-week mark for his 15K, but in just 2 more weeks, he will be able to run over 15K, so good for him. And then it asks, will Tim be able to run a 20K race in 6 months? So there are 52 weeks in a year, so 6 months I said was 26 weeks, and then we just calculated how many kilometers he'd be able to run, okay, after 26 weeks. So all we're doing again is calculating, hitting that calc function on our curve in our calculators, and it gives us an output, and our output in this instance was distance. Okay, so we can see down here that that distance is going to be over 20K. So our answers to this: at 20 weeks he cannot run 15, but at 22 weeks he can run 15K, and he will be able to run 20K in 6 months, but just barely. All right, so that's it for this lesson. Good luck with your practice.